the cartoon periodic table. If you can count to 4, you can get the charge trends for monoatomic ions. It goes +1, +2. Skip the short column. Just skip them for a second. +3, +4. Now, what does that mean? It means the first column with its 1 valence electron loses it. It's a negative. An electron is negative. So when it loses it, it goes +1. The second column with its 2 valence electrons loses them, and it goes +2. These guys are also +2. They're also +1. We've talked about them. They're exceptions, you know. So just know it could be +2 or +1. There's no, you don't need to memorize anything there. You should know copper and chromium are going to be, you know, the S1 exceptions. We've talked about it. I'm not going to go there anymore. This one has 3 valence electrons, so it will lose 3. This column has 4 valence electrons. It will lose 4. Now, 4 is halfway to the 8. This column has 8 valence electrons. This is the structure we're trying to get to. What is happening up to 4 is that they strip off the outer valence electrons, because underneath that is the noble gas 8 of the earlier lower energy level. Once you get to 4, which is halfway to 8, it becomes easier to gain electrons. So if you look at 5 valence electrons, it becomes easier to use gray here, pick up 3. So this becomes -3. And when you have 6 valence electrons, all you got to do is pick up 2 to get the 8. So that becomes -2. These guys over here have 7 valence electrons. So you only have to pick up 1. Trying to make them different colors so you can see it. So they only go -1. And of course, noble gas is already there, so they don't change. These guys have 2 valence electrons. These guys have 2 valence electrons in general, except for the exceptions. Does anybody not get this trend? 1, 2, 3, 4, -3, -2, -1, 0. Now this is for ionics. When we talk about polyatomics, I'm going to be telling you about nonmetals covalently bonding together, but not having enough electrons to be stable, so they end up stealing. In general, they steal an electron from somewhere, and that's what forms polyatomic ions. Inside the polyatomic ion, typically, one of the nonmetals is more electronegative than the other one, so that one will pull the electrons away from the other nonmetal, and the other nonmetal will then have a slightly positive charge. It's not called an ionic charge. We call it an oxidation number, because when you lose electrons, if you remember last class lecture, I told you oil rate. Oxidation is loss of electrons. If you're covalently bonded to a nonmetal that is more electronegative, it will pull your electrons away from you slightly, leaving you somewhat positive. You've been oxidized by the other one that you're joined to. And you will have a partial positive charge called an oxidation number. We'll talk about that more in a minute when I hit the polyatomic ions. When I do, if you look down the page, you will see this chart, but you will see that it has been modified to add +5, +6, +7. And those are non-metal covalent oxidation numbers. They're synonymous. They're very much like charges, but they're not completely charges because they didn't completely lose the electrons. They're sharing them. So non-metal covalent oxidation numbers. But you'll notice the trend just continues, counting the valence electrons. 1, 2, 3, 4, 5, 6, 7. So if you can understand that the +5, +6, +7 are, you know, they're not charges of ions. You're not going to see ions +5, +6, +7. That's just inside covalent bonds. You're going to see that. Now we'll talk about it. Let me keep moving. In today's notes, is it calcium bromide or calcium nitride right underneath there? I think it's calcium nitride, right? Okay, so let's say we're given this name, calcium nitride. Couple thoughts here. First of all, the metal always goes on the left. And it's not just the pure metal. Remember that the metal divider goes like this. Okay, it's not just the pure metals that are over here. In general, when you stick 2 things together from the periodic table, whether it be ionically or whether it be covalently or even whether it be metallic bond-like, whichever one is to the left of the periodic table goes to the left of the formula or the left of the name. Thank you, Ashley, for writing that down. Whichever one is on the left of the periodic table tends to go to the left of the name. So you'll see calcium lives over here and nitrogen lives here. So that's how you write it, because calcium is to the left of nitrogen. It's actually more complicated than that, but it's not that much more complicated. The less electronegative, in other words, the elements get written in order of their increasing electronegativity in formulas, which tends to be whoever's on the right goes to the right of the formula. So calcium's on the left because it has a lower electronegativity. It's on the left side of the periodic table. That was the trend. If you remember, the trend is towards the top right. It increases. Nitrogen is to the top right. It's more electronegative, so it goes at the end of the formula. You'll also notice the metal ion name the metal ion name equals just the element name. That's easy. So you instantly know 80 element or 80 metal ions because their name is the same as the name of the element. Look at the periodic table. You'll have a periodic table with the names on it. If it's a metal, then the ion's name is just whatever it was as an element. Calcium. Don't have to change the name to get the ion. It is the ion. But you'll notice that nitrogen is no longer nitrogen. It's now nitride. So IDE is the monatomic non-metal ion ending or suffix. Whenever you see IDE, not 100%, but 90% of the time, that's still an A. 90% of the time, if you see the suffix IDE, you know you're looking. I'll say 100% of the time, if you see IDE, you know you're looking at the more non-metallish component of a compound. If it's a monatomic ionic compound, it is the non-metal. They end in IDE, carbon dioxide, even though that's not an ionic compound. Oxygen is the more, it's more non-metallic, it's more electronegative, so it gets the IDE ending. Whichever one is more electronegative in the compound is going to get the IDE ending. The one on the right is going to have the IDE ending. You take the root and you substitute, you add to it the IDE. That's how we name things. Sodium chloride, you know that. Table salt, right? Okay. Now, how do we convert a name like this into a formula? First of all, you write the symbol, calcium. Second of all, the next symbol is nitrogen. You write them next to each other. Then you look at the periodic table for the likely charges. Calcium is +2, nitrogen is -3. You write them up there, superscript. If the numbers are the same size with different charges, if they're the same charges, they won't attract each other. If they're both positive, they're not going to attract each other. If they're both negative, they're not going to attract each other. So we expect them to be opposite. It's ionic. So I'm not talking about the charge now. I'm talking about the size. If the numbers are the same, think about it. If it was +2 and -2, they would attract each other because they're opposite. And when they came together and stuck, you would end up with a 0 charge, which means the +2 and the -2 would neutralize each other and stick together, and it would be done. It would be a 1-to-1 relationship. They would have no further charge to attract any other ions. However, many times you will see two ions attract each other because they're opposite, but they will not have the same size. And so when they stick together, they're not done. They can still attract something of the opposite charge. So for example, -3 nitrogen and +2 calcium, when they stick together, they will still have a -1 charge overall, which means it's going to attract another calcium, because calcium is positive. And when a +2 and a -1 join together, you're going to be left with a +1 charge. So that's going to attract another -3 nitrogen. Now you're going to have a -2 charge. So that's going to attract another calcium, which is +2. Boom, 0 finally, right? Now that's complicated. And I'll show you, I'll draw it in a second. But there's a much easier way. Of course, if the charges are the same, it's 1-to-1, 1 and done, as they say. 1-to-1 ratio, boom, you're done. But if the charges are opposite, here's what you do. Angelina, don't fall asleep on this. You bring the number 2, not the charge, down, because we're talking about proportions. That is called the crisscross method. Let me change colors here so you can see what I'm doing. You bring this charge and crisscross it down to here, and you bring this number and bring it down to here. And what that tells you is it takes 3 positive 2s to balance 2 negative 3s. It's called the crisscross method, and it works 80 to 90% of the time. As you study it, you'll figure out how to make it work 100% of the time. And it's still never 100%, but it's up there. It's 90, 95%. It's an 8. It's called the crisscross method, and it produces the most likely formula for a ionic compound. And we're talking about monoatomic ions right now. Calcium is a single atom. Nitrogen is a single atom ion. So we have this calcium nitride name. We know it's single because it ends with IDE. And we know what the charges are from the positions on the periodic table that you're supposed to memorize. It's very simple. 1, 2, 3, 4, -3, -2, -1, 0. You check to see if the charges are the same size. If they are, you click them together and it's done. I'll show you that in just a second. If they're not the same, you crisscross the opposite sides. The superscripts charge numbers become the subscripts of the opposite elements. So let's take a look at that. I'm going to change page. Let's do that again. Calcium nitride. That's Ca, that's N. Likely charge +2, -3. We say those charges are not the same size. So I'm going to bring the 3 down, just the number, not the sign, because I'm looking at proportions. Look, that's a 3, and that's a 2. So I get Ca3N2. Now, I can illustrate this. I can show it algebraically why that works. You're not going to want to do it the algebraic way. I can also show you with drawing Legos why it works. You're not going to want to do that during a quiz. You won't have time. This is the fastest way to do it. Algebraically, calcium +2 and nitrogen minus 3 will attract towards each other. When they stick together, you'll get calcium, nitrogen, minus 3 plus 2 is minus 1. And what that will do is it will attract another oppositely charged calcium. It will come towards that because this is negative, this is positive. You will now have Ca2N, and plus 2 minus 1, it'll have a plus 1 charge. Well, that's going to attract, a plus 1 is going to attract another N minus 3 because that's negative, that's positive. You will now have Ca2N2, whoops, let me change colors. And minus 3 plus 1 is minus 2. Well, that's going to attract another calcium plus 2. So you end up with Ca3N2 with a 0 charge. Once it hits 0, it will not attract any opposite. There won't, there's nothing opposite to 0. It won't attract any more ions. That's how that works. You can draw it. Calcium. You can draw it like a Lego. If you think of, if you think of the protrusions on a Lego as positives, then that would be plus 2. And here's nitrogen with its minus 3. These are recesses. This is nitrogen with 3 recesses, nitrogen minus 3. So what's going to happen is this is going to stick in there. So we get this. The calcium plus 2 sticking in there. But there's still a recess, so that will attract another. There we go. That'll attract another calcium. That's now you got a protrusion here that will attract another nitrogen. And that's going to attract, because there's leftover recesses, that'll attract yet another calcium, and you'll get that. So it takes 3 calcium plus 2s to fill 2 nitrogen minus 3s. That's in your notes. If you, I don't think that's in your notes yet. It'll be in your notes today. I'll put it in the notes today. But really, this is going to do it. I mean, you don't want to sit around drawing pictures and stuff. It's called the crisscross method. If you Google or if you look on YouTube for the crisscross ionic compound formula, you'll find it. Crisscross method. Okay. Does anybody have a question about that? Let's look at this. Calcium oxide. What do we do with that? Well, there's the periodic table. Plus 1, plus 2, plus 2, plus 1. Plus 3, plus 4, minus 3, minus 2, minus 1, 0. Oxygen lives here. Calcium lives here. Wow, what do you know? Ca plus 2, oxygen minus 2. They're the same size. You do not crisscross when they are the same size, Emily. That number is the same size as that opposite charge, the same size. So what happens? They attract each other. They shut each other down. They neutralize each other. This cannot attract another calcium, cannot attract another oxygen. So it's done. It's done. Let's try this. Aluminum chloride. See if you can figure that out on paper or on your notes. Aluminum chloride. Don't Google it. Anybody can Google it. If you Google things, you'll never be more than a technician working for somebody else. If you figure out how to do it, you'll be the manager. You'll be the supervisor. You'll be the one that tells other people what to do. Don't just Google it. Figure out why it works. Then you can tell other people. Because things change. That doesn't change, but the ions will change. You'll run into another situation where you have to apply the technique. Like I said, if you can't, you'll never be more than a technician. Which is okay if that's what makes you happy. If you want to own your own business, if you want to be the boss of a business, if you want to be the doctor, if you want to be the head nurse, then you need to understand why things work. You can tell other people, yes, that's right, no, that's wrong. What do we think? What's the charge on aluminum? What's the symbol? Al. What's the charge? Plus 3. What about chlorine?
Minus 2. No, minus 1.
What's the symbol?
Cl.
And minus 1, you said?
Yeah.
Okay, notice they're not the same. That one comes down here. This one comes down here. We get Al1, Cl3. Now, just like in algebra, we don't need to show coefficients and subscripts that are 1. So it's just Al, Cl3, aluminum chloride. Okay. Now, let's talk about polyatomic ions. Because everything we just rehearsed with monatomic compounds works with polyatomic compounds. So, ionic compounds. Does anybody have a question, first of all? Before I change pages, does anybody have a question? Wow. Okay. We're going to talk about chlorate. You should have memorized chlorate. I asked you to memorize all the polyatomic ions in those tables that ended in ATE. I told you if you did, then you would come into class today and I would show you how to multiply what you memorized by 3 or even 4. I'm going to show you how to turn this single polyatomic ion into 20 ions. All right. So the first step is to understand that this is a halogen ion, making the periodic table look like this. These are the noble gases. These are the halogens. They're called halogens, if you didn't hear me months ago say it, because they're the primary components in salt water, seawater. If you take a bucket of salt water and you accidentally slosh it and some spills on a rock or a smooth surface, after the water evaporates, it will leave a ring of salt, a circle of salt. And in Greek, that is called a halo. And gen comes from the word to generate or to make, same as gene or genetics, generate. So the halogens were isolated from the salt circle that was left when you spilled water or deliberately poured water or splashed water. You could then scrape up the solids and you could melt it, run electricity through it, and separate it out. And you would get fluorine, chlorine, bromine, iodine, and acetylene. So these are the halogens. And for the halogens, every single halogen can be substituted in by taking the root of them. Fluor, chlor, brom, iode, and astatine. So you could make this 8, 8, 8, and 8. Now you memorize chlorate, I hope, as ClO3 negative. You do the same thing. You substitute the symbol for fluorine, and you get FO3 negative. Substitute the symbol for bromine, and you get BrO3 negative. Notice the charges are the same, the number of oxygens are the same. IO3 negative, iodate. ATO3, acetate, negative. They all have the same charge. They all have the same proportion of oxygens. So if you learn chlorate, you've learned 5, 1, 2, 3, 4, 5 ions. You could also do S, unum septi, which actually has a name now, I believe, but it doesn't exist. It doesn't exist in nature. 117, element 117. What's the name?
117.
Yeah, I thought you were looking it up. No.
Oh no, 117.
All right. So it's UUS is the old symbol for it, but I believe there's a name. No, let's drop it. Let's move on. Let's move on. All right. So does everyone get that you can take the symbol and the root for any halogen and substitute it in for the symbol or the root of chlorate or chlorine and chlorate, and you get the same exact named ion, but for different halogens, right? They would call that halate. In the generic form, all of these are halates. If you were an oceanographer, you might talk about the total concentration of halates in the ocean. In which case, you'd be talking about fluorates, the chlorates, the bromates, and the iodates, and the acetates together. What's that? Miguel's a halate? Don't halate on him. All right. So let me show you what you can do with chlorate now. This is not just true for chlorate. It's also true for all the halates, but it's also true for all polyatomic ions that end in ATE. I'm going to show you how to multiply now the 8s into the ites and to others. So chlorate has this formula, ClO3, -1. If you remove one oxygen, you will now have ClO2. Notice that it has the same -1 charge. This is chlorite. In fact, the ite ions that end in ITE. Now it's difficult because sometimes people talk and you can't tell if they're saying ITE, ite, or IDE, ide. You have to ask people, can you clarify? If you do not hear them clearly, you must ask them because it's a big difference. ITE ions are one less oxygen than ATE ions. Okay.
Stand for something, or is it just
what?
Does the ATE stand for something?
200 years ago, maybe. I don't know now what it meant. We've inherited. If you look at the development of chemistry, it came from alchemy, and there were people in France, there were people in Germany, Italy, there were people all over Europe, and they all developed their own names for things. And so you'll notice that it's very chaotic. The naming in chemistry is chaotic. And I'm doing, we've done our best to try to look for some similarities to give you some kind of structure. Maybe 100 years from now, we will completely leave behind the randomness that we've inherited and move to like the system up there where you see like 117 is un septium. Well, where does that come from? Uno sept is 7, 116 un hexium, 116 hex. But right now, this is what we have. All right. If you notice, you can still remove another oxygen because there's 2 of them there, and you will have this, and that exists. That is the active ingredient in household bleach. If you remove one oxygen from the ite, then the number of oxygen you have is 1 below the ite number. And the Greek word for below is hypo, as in hypodermic, is a needle that goes below your skin, right? Hypodermic is a needle that goes below your skin. The Greek word hypoglycemic, means you have low blood sugar. So we put the prefix hypo, and then we write chlorite. And what that means is that this ion is below the chlorite in oxygens. You removed one oxygen, so this is one below the chlorite. Hypo blank ite ions are one oxygen less than the ite, or two less than the 8. I think that's what my notes currently say, 2 less than the 8. But it's 1 less than the ite, and that connects it with the ite name. That's why it's hypoite. Now notice what happens. Notice what happens when you remove the last oxygen. You're at chloride. That means there's no oxygens on it. It's just the naked monoatomic ion. So there, if you're looking at that, we have just converted chlorate into 4 total ions just by manipulating the number of oxygens. But wait, there's one more. What happens if we add an oxygen? As it turns out, you can add one more oxygen. That's the end, really. I mean, you could. That's really the end, the practical end. You could imagine just continuing the process, but it gets impractical. Well, since this is one more than chlorate, what's the Greek prefix for when something is above something? Like if you're above average in energy, what do they call you? Hyper. Hyper. You're so hyper, settle down, because you're above average. You're above the normal energy levels. Hyper. Okay. Hypertension. Blood pressure is high. It's above average. I don't know if there's hyperglycemic. I'm sure there is. So hyperchlorate. But we don't say high anymore. Over the years, the high part of that has dropped out. So we just say perchlorate, but it came from hyperchlorate. Too many syllables, I guess.
This is, yeah, hyperglycemia.
Means you have high blood sugar?
No, I just searched it up.
What does it mean?
I just searched it up.
Oh, okay. It should mean you have high blood sugar.
Hyperglycemia.
Hyper.
Hyperglycemia refers to high levels of sugar.
Yeah. So hyper means above average. And so the 8 ions, I'm telling you, the 8 ions are the average ions. They are the average ions. Typically, the ATE ions are the ions that give the root element, in this case chlorine, its octet. And these other ions are semi-stable versions where they have full sublevel or a half full sublevel. See that word? Those words keep coming back to haunt us. Semi-stable. You know, it's the mountain. The mountaintop is very unstable. It's the element without an octet. And then when you get down to the first ledge, you're like half full sublevel. That's like, okay, I borrowed some electrons, I'm sharing some electrons, but I'm not at my octet yet. Maybe you're at the hypoite version. And then you borrow some more electrons, you share some more electrons. Now you're at the ite version. So maybe you're like a full sublevel. When you finally get to the ATE, you get your full S2P6 octet by sharing and borrowing electrons. I don't know what to tell you about the perate. It's always bugged me, but it's there. And there's even a Cl2O. I think there's a Cl2O5 or something crazy like that. All right. Now you have 5 ions by memorizing chlorate. Because you have the perchlorate, you have the chlorate, the chlorite, the hypochlorite, and of course you've got the chloride. But remember, for the halogens, you can simply substitute in any of the other halogen. For example, brome. And that would be BrO4 -1. Perbromate. You could put in, this is my favorite, because my favorite halogen, polyatomic halogen, because it actually makes kind of like a word. What if I put in iode? Then I get per-iodate, and it looks like periodic. Looks like period. IO4. And when it becomes an ion, it becomes periodic. I mean, when it becomes a compound, it becomes periodic. So it's kind of, anyway, so guys, right there from chlorate, you now know 20 ions, because each halogen is worth 5. Actually, 25, because there's 5 naturally occurring halogens. Does anybody online have a question? Let's try naming some ions. Let's try writing formulas for polyatomic ions now. Let's do this. Let's do sodium. Sodium looks like an integral from capital. Sodium sulfate. Okay, and you should have memorized sulfate. SO4 2-. So Na, first column, +1. Sulfate, you would have memorized as SO4 2-. You can't really tell that. Well, I guess you could. If you look at the sulfur column, it's the -2 column. But it doesn't always work like that. Nitrogen doesn't work like that. Nitrate is -1. Okay, so These charges are not the same. So what we end up doing is crisscrossing the 2 down here and the 1 down here. Now you can't leave it like that. That looks like 41. That would be wrong. Well, fortunately, we don't need to show 1. So it just becomes Na2SO4. Sodium sulfate. Anybody have a question on that? Let's do aluminum sulfite. What's the symbol for aluminum? Al. What was its likely charge? We did this earlier. +3. Now, sulfite is related to sulfate. It's 1 less oxygen, right? It's the ite. So if you learned that sulfate is SO4, then this has to be SO3, and it still has the -2 charge. All of the family members have the same charge. Now, these numbers are not the same, so we're going to crisscross them, but we have a problem here. That 3's got to stay, and there's no such thing as SO33. So what we have to do is we have to put parentheses around this. And I like to say this is the identity subscript. That's what distinguishes it from sulfate to sulfite, the identity subscript. This is a Beightol-ism, and this is the quantity subscript. It tells you how many of those you have to have. So you end up with Al2SO3, 3. This means there are 3 sulfites attached to 2 aluminums. 3 sulfites attached to 2 aluminums.
What's that word with the 3 other parentheses?
This is identity subscript. This is quantity subscript. That's my vocab. I've never seen anybody else. There might be another technical name for distinguishing between those two. That's how I distinguish between them. All right. And I call that the identity because if it was SO4, it would have a different name. It would be sulfate. So that's part of its identity. This just tells us that there are 3 of them. Now we can do this in reverse. Let me pop the notes up there. Scrolling down. Okay, so there's a written explanation of the crisscross method. There's your polyatomic ions. There's my notes on how they're related. There's more notes on how they're all related. Everything, if you read this right here, it will now make sense to you. I want to talk about these oxidation numbers, the 5, 6, and 7. We'll close on that. Is that what I want to do? Yeah, that's what I want to do. So I'm going to go ahead and go back to that. There's no periodic table. I'm just going to count all the way across to 0. These are oxidation numbers. What are oxidation numbers? I'm going to say it verbally. In covalent compounds, when the electronegativities are not the same, which is typical. The only time you're ever really going to bond to something with exactly the same electronegativity is when you bond to your identical twin, like arm wrestling your identical twin. Every other element on the periodic table is slightly different from every other element. So no matter who bonds to whom, there's going to be a slight difference in electronegativities. So one of the elements is going to get the electrons more than the other one. The one that gets it more is going to be slightly negative. The one that gets the electrons less is going to be slightly positive, and that's what these charges are. So if you put nitrate, NO3 negative, and you look at the fact that nitrogen is here and oxygen is here, here's what I want you to realize. Oxygen's to the right, that means it will be the negative one. It's written to the right, it's the negative one. So if this is going to be -2, watch what I'm going to do. The sum of all the oxidation numbers equals the charge. Well, the charge is -1. So watch what I'm going to do. Nitrogen plus 3 times oxygen, there's 3 oxygens, will equal -1. Oxygen being to the right will get the negative number, 3 times -2. Nitrogen plus 3 times -2 equals -1. And we'll see that nitrogen -6 equals -1, or nitrogen equals +5. And you can see that nitrogen, when it's in the nitrate version, on the left side, is going to be +5 oxidation number. You need to know this statement. That's a very important statement.